Hello everyone, welcome back to our physics classes. Today we are going to explore a very interesting concept from Newton's first law of motion, and that is inertia of rest. Look at the definition on the screen. An object at rest will remain at rest unless an external force is applied. This means objects are naturally lazy. They resist any change to their peaceful state of rest. Let's understand this with two super fun real world example. Let's look at our first activity. Imagine placing a smooth card over a glass and putting a coin on top of that card. Now, what happened if you flick the card suddenly and very quickly? The card flies away, but the coin doesn't. Instead, the coin falls straight down into the glass. Why? Because of inertia of rest. The force was applied only to the card so that the card moves, but the coin wants to stay right where it was. So it fell vertically into the glass. Now look at the second example, which you all must have seen while playing carom. When you make a neat pile of carom coin and hit the bottommost coin very hard and fast with striker. What happened? Only the bottom coin shoots out, the rest of the pile stays perfectly intact and drop straight down onto board. This happens because the striker only transfer force to the bottom coin. The coin above it remain at rest due to inertia of rest and just fall vertically downward. Now next slide. Okay, the bus passenger. Look at the first scenario on the screen. Have you ever noticed what happened when you are standing in a stationary bus and it suddenly starts moving forward? You instantly fall backward. Why does this happen? Because of because of the inertia of the rest. When the bus moves forward suddenly, the lower part of your body, which is in direct contact with the bus floor, moves forward along with it. However, the upper part of your body wants to stay at rest due to inertia. As a result, your upper body stays behind for a moment, causing you to fall backward. Now, shaking a tree branch. Now let's look at the second example. What happened when you vigorously shake branch of a tree? Some leaves and ribs fruits detached and fall straight down onto the ground. Here is the physics behind it. When you shake the branch, you apply an external force directly to the branch so that the branch moves, but the leaves and fruits have inertia of rest, so they try to maintain their original position of rest. Because the branch moves away while the fruits try to stay in place, the weak joint break and gravity pull the fruit down. Now let's look at two more highly practical examples of inertia of rest. First, jacking wet clothes. Look at the first activity on your screen. Why do we give wet clothes a sharp jack before hanging them on the line to dry? This is done to separate the trapped water droplets from the fabric. When you give a sudden jack to wet cloth, you apply an external force directly to the cloth's fabric, causing it to move suddenly. However, the water droplets trapped inside possess inertia of rest. They try to maintain their position of rest because the clothes moves away quickly while the water droplets stay where they were. The droplets separate from the clothes and fall down. Now look at the second example, which is a classical board exam question. And when a dirty carpet is beaten hanging on line with a stick, dust particle immediately fly out of it. Why? The physics explanation is very simple. When we hit the carpet with a stick, our fabric makes the carpet fabric move backward or forward, but the dust particles stuck on it want to remain at rest due to inertia of rest. As the carpet fabric move away from its position, the dust particles are left behind in air, lose their support, and gravity pull them down to the ground. Further, next slide. Here we are going to study inertia of motion. Look at the picture on the screen. Have you ever noticed what happens when you are standing in a moving bus and the driver applies the brake suddenly? You instantly lurch or fall forward. Why does this happen? Let's look at the physics behind it. When the bus is moving, your entire body is moving along with it at the same speed. But the moment the driver hits the brakes, an external force applies the bus. Because your feet are in direct contact with the bus floor, your legs and feet come to rest immediately. Along with the bus, however, the upper part of your body is still in moving due to inertia. It wants to keep moving forward at the same speed. Because your lower body stops but your upper body keeps moving, you fall forward. Now we are going further for the next slide. Let's look at a very important life-saving application of inertia of motion. Look at the image on your screen. When a car is cruising down the road, your body is moving forward at the exact same speed as the car. But what happens if the driver has to stop on the brakes and stop suddenly? Even through the brakes stop the car, your body wants to keep moving forward at the original speed due to inertia of motion. Without anything to hold you back, you could violently collide with the steering wheel, the front dashboard, or even crash through the windshields. This is where the safety belt comes to the rescue. It applies an opposing external force on your body, stopping you from flying forward and preventing several injuries. Now, we are going to start a fresh and incredibly important topic in this chapter: momentum, denoted by the capital letter P. Think of momentum as the impact or the quantity of motion contained in a moving body. Why is it harder to stop a cricket ball than a tennis ball thrown at the same speed? Or why does a tiny bullet cause so much damage? The secret line lies in this one concept. Let's look at the formal definition and formula on the screen. As you can see on the slide, momentum is defined as the product of mass and velocity. Mathematically, we expressed it with a very simple formula: P is equal to mass into velocity. Here P stands for momentum, m is the mass, and v is velocity. Now note down two crucial properties for your board exam. First, momentum is a vector quantity. This means it doesn't just have a value or magnitude, it also has specific direction, which is always the same as the direction of the velocity. Second, its SI unit is kg meter per second. You get this simple by multiplying the unit of mass with the unit of velocity. Let's solve a quick numerical together to see how this formula works in exam. Look at the problem on the screen. Calculate the momentum of a bullet of mass 0.02 kg moving with speed of 1000 meter per second. First, let's write down the given values. Mass m is equal to 0.02 kg, velocity v is equal to 1000 meter per second. Now we apply our golden formula: P is equal to mass into velocity. Substituting the values, we get 0.02 into 1000. When we multiply this, our final answer comes out to be 20 kg meter per second. See how simple that was.